Alright everybody, this video has sound, so hopefully you're getting the sound up and running. If you're just watching it and you're seeing me point at this sign, because sound is important. Alright, so this is a lesson on skill 12.4.1, that's chapter 12, section 4, part 1, finding volumes of prisms, out of the chapter 12 geometry study guide. Okay. So, volume basically is an amount of three-dimensional space. So, when we think about space, we think of how much space our bodies can take up, or how much air you can put in a room, or how much hot air you can put in a hot air balloon. It's basically volume is an amount of like liquid or gas, anything that you can measure in 3 dimensions. That's volume. So cubes are like a Rubik's cube. It has a square on each side, and there are 6 lateral square faces. The volume of a cube is basically an extension of the volume of a square. Remember, volume, or the area of a square. The area of a square is just side times side, right? But that's because a square is just a 2-dimensional object. When we add a 3rd dimension, we not only have length and width, but we also have height, basically, or the 3rd dimension. So this one, because it's a cube, it has 3 dimensions, would have a width of s, a length of s, and a height of s. So to find volume, it's just side times side times side. You could also think of that as side cubed. These postulates down here aren't super important, but when you have a 2 polyhedra, that is a 3-dimensional object where all the sides are flat surfaces, when they are congruent, then they have the same volume. That makes sense. If you have the same size and shape of 2 objects, they're basically identical, then they're going to take up the same amount of space, which means they have the same volume. Postulate number 29 says the volume of a solid is the sum, meaning adding together, of the volumes of all its non-overlapping parts. Basically, that means that if you take a 3-dimensional object and slice it in 2 pieces, adding up the surface or the volume of the 2 pieces is the same as the volume of the whole thing put together. It's kind of a silly one, but it's like the 2 parts equal the whole thing. Yeah. And then you can have more than 2 parts, but basically all the little pieces add up together give you the total volume for the whole thing if you cut it up in pieces. Theorem 12.6 is the volume of a prism. Now a prism, again, is basically where you've got a lot of right angles going on there, and you've got a top and bottom base that are identical. So basically, if you take length times width times height, length times width times height, you have the volume of that prism. Now, another way to say this is that because length times width is the area of the base, they use big B for area of the base, and then you multiply that by the height. And, I just noticed they use little h for height, so I'm going to do that too. Length times width times height, little h. But it's really just the height of the object. Okay. So let's see what we can do. Okay, now this first object has been tipped over on its side. The way that I know this is that prisms have to have a top and a bottom that are the same and that are parallel to one another. So do you see this base right here doesn't have a parallel side above it, this rectangle? That's how I know that's not the base. The bases are actually the triangles on both ends. Do you see how they're the same shape and they're parallel to one another? That is how I know that this object has been knocked over on its side. So what I'm going to do in my head is I'm going to take this shape and I'm going to tip it right side up, which means that this triangle is going to be the base, and then this is going to be the height. Okay? So I've identified the height as 2, and then the base, I'm going to need to find the area for that, because the formula for a volume of a prism is area of the base times the height of the object. So this base is a triangle, right? And the area of a triangle is 1/2 base times height. Now this is the base of the triangle and the height of the triangle, not the base and the height of the object. That's different. So the base of the triangle is 3 units long, and the height of the triangle is 1 unit long. So basically 1/2 times 3 times 1 gives you 1.5 square feet for the area of the base triangle. So the volume of the whole object, meaning how much space does this entire object take up, is area of the base, which is 1.5 square feet, times the height of the object, and again this has been knocked over, so if I tip it straight up, then this would be the height, which is 2. So the volume of this right triangular prism is 1.5 times 2, or 3 cubic feet. This right rectangular prism, area of the base times the height. The base down here is a rectangle. I know that because they call it a rectangular prism. The area of the base would be length times width, or 11 times 4, right? And then the height of the object is 5. So if I multiply 11 times 4 times 5, I get 220 cubic meters. Notice that it's cubic meters, not square meters. When we're measuring just a surface, we measure that area and we write square units on it. Square feet, square inches, square meters, whatever. When we're talking about how much space something takes up in 3 dimensions, then we use cubic units. All right. Now the last example, this shape is not standing perfectly right. The bases are actually the hexagon in the front and the back. And you can see that these front and back shapes are identical, and all those little lateral faces are connecting them at right angles. So that's how I know that those are my bases, and then all these side parts should be standing straight up and down like walls. So this object to me is kind of pushed over on its side. So if I take it and I put it straight so that the base here is what it's sitting on, then this length here would actually be the height. So the height of the entire object sitting straight up and down, not knocked over, would be 5 centimeters. Now that's good to know, because to calculate the volume, which I'm assuming they want us to find, is area of the base times the height of the whole object. So the height is 5. Now, how do we calculate the area of the base? Well, when it's knocked over like this, the base is actually the front of it, and this is a hexagon, and it's a regular hexagon. How do I know it's regular? Because all 6 sides are marked congruent. There's actually a formula for the area of any regular polygon, and that is 1/2 apothem times perimeter. We learned that back in section 11.6 in the beginning of this packet. So the perimeter isn't too hard to calculate. This side length is 8. There's 8 here, 8, 8, 8, 8. So to calculate the distance all the way around, that's the perimeter, we could add 8 to itself many times, 8 plus 8 plus 8 plus 8 plus 8 plus 8, or we could just say that the perimeter is the number of sides, which is 6, times the length of each side, which is 8. So our perimeter is 48 units around the outside of our base. Now we just have to figure out how long the apothem is. The apothem is the distance from the center of the base straight down to the middle of one side. And that is when we draw that out, we actually carve this triangle into two right triangles. Now that triangle right there, this length right here is half of the length of that side. So if that's 8, then this half of it would be 4. And then up here, the central angle actually goes from here to here. And if I drew in all the radii, you would see that there is 1, 2, 3, 4, 5, 6 of these central angles inside this circle. And they're all the same as each other. They're congruent. So to find the central angle going across from here to here, I could take 360 and divide it by 6 to get 60 degrees. That's the distance in degrees from here to here. But on my triangle, this little angle up here is half of that. So that's why this angle up here is 30. So what you could do is you could recognize this triangle as a 30, 60, 90 triangle and then say, oh, this is the short side. And if I want to find the long side, that would be the square root of 3 times that much. Or you could use trigonometry. You could use this as your reference angle. This is your opposite side. And then to find the apothem length, you could use that as your adjacent. You could use tangent to find this. One way or the other, you should find the apothem to be 4 times the square root of 3 in length. So over here, I will place that as a substitution for my apothem, my actual value. So if I take all of this as the area of my base, and I'm going to try to simplify that just a little bit. I think that's 96 root 3, right? Because it'd be 2 times 48, yeah. So if you have half of 4, that's 2, and then 2 times 48 is 96, and then bring down the square root of 3, that would be the area for the whole base here, that is our hexagon, our regular hexagon. So that'd be 96 root 3. So if you multiply 96 times 5, now we're finally calculating the volume of the entire object, how much space it actually takes up. 96 times 5 is 480. So 480 times the square root of 3 cubic centimeters would be the exact answer. But if you wanted an approximated answer, you could take the square root of 3 on your calculator and multiply it by 480. Which would give you about 831.38 cubic centimeters. So sometimes when we're using numbers, it's helpful to have exact answers, especially if this number is going to be a number we're going to use elsewhere. We don't want anything rounded off or approximated. We want the exact number. Other times, we really just need to know, as close as we can, you know, to a couple decimal places, how much it is. If we're ordering, you know, a certain amount of glue that we need for a project, we need to know how many cans of glue to buy, so we need to know this number, not that one. So it all depends on the kind of ways that you're going to use the number in that makes one answer better than the other, the exact versus the approximated. And you just kind of make the decision when you need to make the decision. Which one is better?